This one molecule, now drawn a total of 4 times, it is meso. Welcome, OChemNinjas. As we move through organic chemistry, we're going to be asked to classify molecules. Sometimes we'll be asked to look at a pair of molecules and to classify the relationship between those two molecules. Other times we'll be given a single molecule and asked to describe that single molecule. There are different classification words we use when describing a pair of molecules, separate from the words we use when we describe a single molecule. And if we're not careful, those words can get very confusing and all sound very similar over time. I don't always think organic chemistry professors do a good job separating out the relationship words from the descriptor words. And then, if we're not careful, we might try and use a relationship word to describe the relationship between two molecules. We might try and use that word and apply it to a single molecule, and that's really not appropriate. So I want to be very careful and be very sure we're using the correct type of word in the correct situation. So, to be clear, a relationship word is a word that describes the relationship between two molecules. And by contrast, our descriptor words describe a single molecule. And if you're describing the relationship between two molecules, it is inappropriate to use a descriptor word. So how do we know which word we're supposed to use in which situation? Let's start with just the relationship words. As you get better at this topic, you'll be able to look at molecules and see the relationship word more quickly. But as we're just starting out, I have a hierarchy of questions that you can go through in order to figure out the correct relationship term between two different molecules. Again, we're comparing two different molecules for relationship words, but when we compare those two molecules, we look for these differences, and the differences will tell us which relationship word to use. The first analysis, when comparing two molecules, do they just have different molecular formulas? A lot of different molecules just have different molecular formulas. Take, for example, ethanol versus methanol. These two look like they should be related, and they are, they're both alcohols, but when you look at the molecules from a chemistry standpoint, they have different molecular formulas. Ethanol has 2 carbons, methanol has 1 carbon. These molecules have different molecular formulas. If the molecules have different molecular formulas, that's a fairly easy case. The analysis is over. We call these different molecules. They're different molecules. They have different molecular formulas. Most random molecules in the world are going to be different molecules. Most molecules have different molecular formulas. But most pairs of molecules on an exam are not going to be different molecules. It will rarely be this easy on an exam. So let's look at different relationship words. As the next level of analysis, if we are comparing two molecules and they have the same molecular formula, do they only differ in their connectivity? Different atoms connected to different other atoms. For example, ethanol versus dimethyl ether. They both have 2 carbons and oxygen, but one has an oxygen directly bonded to a hydrogen. This molecule has an oxygen directly bonded to 2 carbons, whereas ethanol only has oxygen bonded to 1 carbon. They have the same molecular formula, they only differ in their connectivity. When they have the same molecular formula and they only differ in their connectivity and their constitution, how they are constituted, how they are connected, we call them constitutional isomers. When comparing two molecules, if they have the same molecular formula, if they have the same connectivity, do they only differ in their location of pi bonds and lone pair electrons? For example, if I introduce a double bond and a negative charge, these molecules have the same molecular formula, they have the same connectivity, carbon-carbon oxygen, carbon-carbon oxygen. They only differ in the placement of the pi bond and the lone pairs between the molecules. If they only differ in pi bonds and lone pairs, they are resonance contributors. If they're resonance contributors, then we should be able to draw a set of curved arrows to convert one into the other. We could take this lone pair from oxygen and make the pi bond, break the pi bond and put those electrons onto the carbon on the left, and that would make these resonance contributors. Our next level of analysis, if we're comparing two structures and they have the same molecular formula and same connectivity, they don't differ in their pi bonds and lone pairs, but they only differ in rotations about single bonds. The relationship word to use in this case is conformational isomers. Any molecule can have a conformational isomer by doing a 120 or 180 degree bond rotation, but we most often encounter conformational isomers in staggered versus eclipsed Newman projections or in chair flips. These molecules have the same molecular formula and same connectivity, they only differ in their rotation about sigma bonds. To get the Newman projection to switch, we just have to rotate the back carbon to make it eclipsed. To change chair structures, all we do is rotate the single bonds in the chair in order to make the new chair flip. They only differ in their rotation about sigma bonds. Our last category of relationship words has to deal with the three-dimensionality of the molecule. If they have the same molecular formula and same connectivity, if they're not resonance contributors or conformational isomers, do they only differ in their three-dimensional arrangement in space? Looking at the two versions of 2-butanol, in one case the OH group is on a wedge pointed towards you, in the other case it's on a dash pointed away from you. We cannot convert these molecules through single bond rotations, they differ in their three-dimensional arrangement in space. The relationship word to describe these molecules is stereoisomers. But we never stop at stereoisomers. Stereoisomers is an umbrella term, and there are different kinds of stereoisomers. If we find ourselves in this situation, we should not write stereoisomer as our answer. We should look further and look at what kind of stereoisomer it is. If we decide that a pair of molecules are stereoisomers, We can next look and see if all of the R and S stereocenters change their configuration. That is a mnemonic way of looking at this relationship. You may not have gotten to R and S stereocenters yet in your course. If you haven't, don't worry about it. The textbook definition of non-superimposable mirror images has two parts to it. The first part is non-superimposable. That means two molecules cannot be completely overlaid on top of each other and be identical in all respects. These two molecules are lined up in the same orientation left to right, but if we slide one over on top of the other one, they don't completely line up. The carbon chain lines up, but the oxygens are pointed in different directions. These molecules are not superimposable. There are lots of molecules that aren't superimposable. To fit this relationship word, they need to be non-superimposable mirror images. That means we should be able to take one and rotate it and manipulate it into being a mirror image of the original. If I take this molecule and I do a 180-degree pancake flip of the molecule, if you're not comfortable manipulating molecules, you can watch my Manipulating Molecules playlist that I've linked down below. The pancake flip of this molecule moves the oxygen to the right side of the molecule and flips it onto a wedge. These molecules are now mirror images of each other. So they are non-superimposable and they are mirror images, or can be manipulated into being mirror images. These are non-superimposable mirror images. The word to describe non-superimposable mirror images, molecules where all of the stereocenters have changed their RRS configuration, is enantiomers. These molecules are enantiomers of each other. I'll also add in a bonus word here, racemic mixture. If you had a flask containing these two enantiomers could be mixed in any proportion, 99% this, 1% that, 60-40, whatever percentage you want. But if you have an exact 50-50 mixture of the two enantiomers, the 50-50 mixture of two enantiomers is called racemic. That is a racemic mixture. The definition of a racemic mixture is a 50-50 mixture of two enantiomers. And it does specifically have to be enantiomers. It can't be a mixture of constitutional isomers or any of the other words we're about to use. It has to be a 50-50 mixture of enantiomers. Our final relationship we're going to look at compares molecules where some but not all of the stereocenters change their R and S configuration. Here, both stereocenters are R, where in the other molecule one is R and one is S. Some of the stereocenters are the same, but some have changed their configuration. Some, but not all, have changed. Again, that's a mnemonic way of looking at it. The textbook definition is actually one of my least favorite textbook definitions in the entire course. The textbook definition of a diastereomer is stereoisomers that are not mirror images. It's just not a very satisfying definition. But we could check that out. These are stereoisomers. They have the same connectivity. They only differ in their three-dimensional orientation in space. And if I try and make them mirror images of each other by doing a pancake flip of the molecule in orange, that does not make them mirror images. It makes them mirror images at the bromine stereocenter, but not at the oxygen stereocenter. So they are stereoisomers, but they are not mirror images, and they cannot be made to be mirror images. The relationship word we use for a mixture of stereoisomers that are not mirror images for molecules where some but not all of the R and S stereocenters change their configuration, we call these pair of molecules diastereomers. No, not disastereomers. Diastereomers. Finally, if you have two molecules and they have the same molecular formula and the same connectivity, and they're not resonance contributors or conformational isomers, and they have the same three-dimensionality, then you just have two identical molecules. You've really just drawn the same molecule twice. Next, let's take a look at the set of descriptor words. As a reminder, descriptor words are words that describe a single molecule. It's inappropriate to use descriptor words to describe the relationship between two molecules. Our first descriptor word is a chiral molecule. We can describe an entire single molecule as a chiral molecule. We can also describe an entire single carbon atom as a chiral carbon atom. A chiral molecule is a molecule with a non-superimposable mirror image. If I try and draw the mirror image of this molecule, this is our universal chemistry symbol for a mirror plane. If I reflect this through a mirror, that reflects the OH group over to the right side of the molecule and keeps it on a wedge. It's a reflection, it's not a pancake flip. Every molecule has a mirror image. It's only a chiral molecule if this mirror image is not superimposable on the original. If I tried to superimpose them now, I wouldn't be able to do so. The oxygens are on opposite sides of the molecule, and the carbon chain zigzags in the wrong direction. But if I do a pancake flip of this molecule, that fixes the zigzag chain and brings the OH group over to the left side of the molecule, but flipping it over moves that OH group onto a dash. They are still not superimposable. There is no way to get the orange molecule to be superimposable on the green molecule. The green molecule has a non-superimposable mirror image. This molecule is chiral. Because the mirror image is not superimposable, that makes this a new molecule too. This new molecule is also chiral. In fact, we saw it earlier, it's the enantiomer of the green molecule. These two molecules are enantiomers. Individually, each molecule can be described as chiral. Together, the relationship between these two molecules is enantiomers. If it were a 50-50 mixture of these enantiomers, we would call that mixture a racemic mixture. Chiral describes the singular molecule. Enantiomers describes the relationship between these two molecules. Your hand is also chiral. Your two hands are mirror images of each other, but they're not superimposable. If you try to superimpose the palms together, then the thumbs point in the wrong direction. If you try and superimpose the thumbs, then the palms point in the wrong direction. Each hand individually is chiral. Together, your hands make up a pair of enantiomers. As an aside, we can also refer to an individual carbon atom as a chiral carbon atom. If that individual carbon atom has 4 unique groups attached to it, it is a chiral carbon atom, commonly referred to as a stereocenter. The 4 unique groups attached to this carbon is the oxygen group, the 1 carbon chain, the 2 carbon chain, and the implied hydrogen. Those 4 groups are unique. This is a chiral carbon. This carbon is a stereocenter. Our next descriptor word is achiral. Achiral is the opposite of chiral. If a chiral molecule had a non-superimposable mirror image, an achiral molecule has a yes superimposable mirror image. When I draw the mirror image of ethanol, it reflects the oxygen over to the left side of the molecule. These molecules are mirror images. As drawn, they are not superimposable. But if I do a pancake flip of the mirror molecule, now the oxygen is on the right side of the molecule, and now these are completely superimposable molecules. They're the same molecule drawn twice, 3 times actually. This one molecule drawn 3 times is achiral. Notice how I'm using the descriptor word here. I'm not saying the relationship between these 2 molecules is achiral. That doesn't make any sense. This one molecule drawn 3 times is described as being achiral. Ethanol is achiral. Most achiral molecules will not have a stereocenter. If a molecule does not have a stereocenter, it must be achiral. Every molecule without a stereocenter is achiral, but only some molecules with stereocenters are chiral. Okay, most molecules with stereocenters are chiral, but not all. There's 2 parts to our mnemonic for an achiral molecule. It may or may not have a stereocenter, but to be achiral, it must have at least 1 plane of symmetry, or can be rotated into having a plane of symmetry. Every achiral molecule will have at least 1 plane of symmetry. A chiral molecule will have 0 planes of symmetry. For ethanol, the plane of symmetry is the plane of the screen. The wedge hydrogens and the dash hydrogens reflect across the symmetrical plane of the screen. Our last descriptor word is a meso molecule. Meso is by far the most confused descriptor word in the entire course. It's also the descriptor word that students most commonly try to use as a relationship word inappropriately. You can't call the relationship between 2 molecules meso. That's an inappropriate use of the term. That would be like saying you have 2 meso noses on your face. You can't have 2 noses on your face. You have 1 nose, and it is meso. In terms of definitions, a meso molecule is a molecule that has more than 1 stereocenter and has a plane of symmetry, or can be rotated into having a plane of symmetry. A multi-stereocenter molecule is, yes, superimposable on its mirror image. If we reflect this molecule through a mirror plane, it doesn't look like the mirror molecule is superimposable on the original. But if I do a 180-degree vertical pancake flip of the molecule, the mirrored molecule is completely superimposable on the original. This is the same molecule drawn 3 different times. This one molecule drawn 3 times is meso. It's not always convenient to try and draw the mirror image and try and rotate it to be superimposable, so the other mnemonic is a molecule with more than 1 stereocenter and has a plane of symmetry, or can be rotated into having a plane of symmetry. This molecule doesn't look like it has a plane of symmetry, but if I do a 180-degree bond rotation around this carbon-carbon bond, that rotates the terminal carbon down to the southern hemisphere and rotates the dash OH group up onto the wedge. And now this molecule does have a plane of symmetry. This one molecule, now drawn a total of 4 times, has more than 1 stereocenter and can be rotated into having a plane of symmetry. It is meso. The trickiest part about meso molecules is if you were to look at these 2 molecules, you might be tempted to say that these 2 molecules are enantiomers. They're lined up the same direction, and all of the wedges and dashes have changed their orientation. And you would be correct in that respect, except for one thing. These are the same molecule. I've now drawn the same molecule 5 total times. To prove it to you, if we rotate this molecule like a steering wheel, we can bring that dash group down to the bottom right and that wedge group up to the top left. These are identical molecules. So please be careful when you're drawing molecules, especially later in the semester when these might be the products of a reaction. You might be tempted to write that the product is a mixture of enantiomers, but really these are the same identical molecule. You've drawn one molecule twice, and this one molecule is meso. So one last mnemonic is molecules that look like they should be enantiomers, but the enantiomer is really identical. Meso molecules don't occur very often, which almost makes it more frustrating. They're tucked away over in a corner of organic chemistry, and when they pop back out, if you're not careful, if you're not looking for it, you may miss it and call these molecules enantiomers, when really they are identical molecules drawn twice. So one other trick you can keep up your sleeve for later, a molecule can only be considered to be meso if that molecule is structurally palindromic. Do you know what I mean by that? Do you know what a palindrome is? It's a word that's written the same forward and backward, like the word mom, M-O-M forward, M-O-M backward. Same word forward and backward. If a molecule is structurally palindromic, it's the same forward and backward, carbon, OH, OH, carbon, this molecule then might be meso. All meso molecules will be structurally palindromic like this. But be careful, not all structurally palindromic molecules are meso. Most of the time they'll just be chiral, but sometimes they will be meso. As an example, this molecule is structurally palindromic, but it is not meso. I'll leave it to you as an exercise. If you go through the same analysis with this molecule, you'll find that the mirror image is not completely superimposable. It has a non-superimposable mirror image. That's our definition of a chiral molecule. It has multiple stereocenters, but it has no plane of symmetry. If you try and rotate it into having a plane of symmetry, you won't be able to find one. It is a molecule with more than one stereocenter and no plane of symmetry. That's a chiral molecule. If you try and draw the enantiomer of this molecule, it is not going to be superimposable on the original. The enantiomer is really a different molecule, and it is a chiral molecule. Whew. That is a lot of relationship and descriptor terms. The biggest point that I can emphasize is to make sure you're using relationship words to describe the relationship between two separate molecules, and descriptor words to describe the one single molecule. If you need a brief refresher later on in this course, I have a playlist down below where I've excerpted each term specifically, so you can look at just a short video of just that one term. Go get 'em, ninjas.
Thanks for watching. If you like what you saw today, maybe let your instructor know about these videos, or your friends at other schools. Check out some of these other videos and playlists, see what you like. As always, don't forget to like and subscribe.